So correlation basically is a tool to measure dependence, to estimate dependence. But there is one important thing that I should make clear. Dependence is a broader concept with respect to correlation. Namely, the absence of correlation is a necessary but not sufficient condition for the data to be independent. So, if the data are not correlated, then they are independent. But the opposite is not true. If the data are not correlated, they still might be, okay, sorry, I didn't formulate the assertion well. So basically, what I said correctly is that the absence of correlation is a necessary condition for the data to be independent, but it's not sufficient. So even if the data are not correlated, they could be still dependent, okay? There is one situation in which correlation is equivalent to dependence, and it's the Gaussian case. If we are talking of Gaussian data, then correlation is equivalent to dependence. So basically, this test on the autocorrelation function, if it tells you that there is no correlation, again, you may conclude that if the data are Gaussian, they are independent. If the data are non-Gaussian, then it's likely that they are independent, but you are not sure. Okay? And I want to be clear on this. Correlation is a measure of linear dependence. Linear memory. If there is some non-linear memory, then correlation may fail in identifying it. Let's say that for our purposes, correlation is fine. Okay, so for us, it's good enough. I just want to mention to you that there are other methods for detecting dependence. We are not investigating them. Okay. Okay. Now the question is more practical. Let's suppose that I found some correlation, so I am sure that there is some memory in it, because if I see correlation, there is memory. How can I reproduce it? And let's keep it very simple. So basically, what is the question? The question is that you have variables like qt and qt plus 1 and qt plus something. They are dependent, they have memory. So the question is, how can we reproduce it? Of course, we have to establish a relationship between the probability distribution, as I said before, of q at subsequent time steps. And there is an easy way to establish a relationship between probability distribution, which is establishing a relationship between the outcomes themselves. And let's keep it simple. Let's assume that this relationship is linear. So let me try to write this relationship in this way. Like qt plus 1, qt, sorry, it's equal to a coefficient let me call it phi1, which multiplies qt minus 1 This is a linear relationship. And let me add a random term, epsilon t. But before writing this, let me anticipate a premise. I always forget this. Let me anticipate a preliminary assumption that μ is 0. And this is something that is not strictly necessary. It's just, let's say, it's useful to write the relationship between variables in a simpler way, like I wrote it here. And it's very easy to achieve this situation because whatever is the mean value of Q, if you take from every observation, you take the difference between the observation minus the mean, then you go to a situation where the mean is 0, okay? So let's suppose that you start from observation Q star T, and mean Q star is equal to, let's say, 100, okay? Whatever it is. And then if you write Qt is equal to Q star T minus 100, then the logical consequence is that μq is equal to 0. So it's very easy to achieve the situation in which the mean value is 0. You just have to compute the mean value of your series and then subtract it from any observation. Very easy. Okay, so this assumption is really something, it's the first assumption, conditioning the validity of this model, but it's very easy to achieve. And then with this assumption, this is an idea. Like, let me write any observation as a linear combination of the past one plus a random term. So you may ask me, why do you introduce this random term? Because, of course, this is an imprecise model. A possible reply to this question is, of course, this is a model that is affected by errors. So I can't write just this part here, forgetting the random error, because it wouldn't work. If I want to make it working, I have to add an error, okay, in order to make it work. And this is one possibility. Of course, you introduce memory here. You see, if phi is greater than 0, if qt minus 1 is very high, like a flood, then also qt, which is the subsequent observation, is very high, because it's multiplied by a coefficient which ensures the dependence. Of course, the value of this coefficient should be commensurate to the memory that the series possesses. And we will see how to estimate this value to make sure that the memory is never produced. But this is a very simple solution to express each outcome, not the random variable, each outcome in this way. Okay, and you may say at this stage, but are you sure that the probability distribution is changing? I would say yes, of course, because if you adopt this relationship, you see that each observation is related to the previous one by this relationship itself, which means that the probability distribution of the observation itself is depending on the probability distribution of the previous value. Because let's suppose that here you have several outcomes from qt minus 1, because you take the measurement with several instruments. Then you get several outcomes from qt, so you get a probability distribution for qt, but of course this probability distribution is directly related to the probability distribution time t minus 1. So by doing so, by relating each possible outcome to the previous one, you make sure that you have a relationship between probability distributions. Now the question is, I am reproducing the memory or not? This is another question. We will see now in a moment if the memory is reproduced or not. But indeed, with this very simple relation, we made sure that there is a relationship between probability distribution. There is memory if phi is different from 0. Okay?
Sorry, I didn't understand. The probability distribution is the same for Qt and Qt minus 1?
No, it's related. It's not the same. They are, now to say, they are relatives. Okay? They are related. But you made a good question. Now the question could be formulated in this way. What is the probability distribution of Qt given the probability distribution of Qt minus 1? This is a good question. So what is the probability distribution? Indeed, we have a convenience in making sure that the probability distribution is the same, maybe with different parameters, which strictly speaking means different distributions. But let's say that we have convenience to make sure that the same type of distribution, like log normal, or Gaussian, or uniform, and we have convenience, of course, to make sure that indeed the distribution doesn't change in shape from t minus 1 to t. And then, if we want this, what is a necessary condition for this? If we want to keep the same distribution, I said that there is only one distribution that is preserved after a linear transformation. This is a linear transformation. You see, this error here is again a random variable, but at each time t, it's an outcome. So basically, this is a linear transformation. So what is the only distribution that is preserved? The Gaussian. So let me make a second assumption. The second assumption is that Q and epsilon, and in this case, I should write the capital letters. I don't know how to write the epsilon in capital, but this is capital letter. These are Gaussian. Both of them, even epsilon needs to be Gaussian. Because if it was not, then it's not Gaussian result. If you sum a Gaussian distribution plus log normal, what you obtain is neither Gaussian nor log normal. It's something undefined. Now you may say, but I don't need this assumption, no? You may say this. Actually, you know, it's not very reasonable that you have a change of probability distribution from t minus 1 to t. This is the same process, it's the river flows. Is it reasonable if you go over the Po River that today you have a probability distribution for the river flow and tomorrow another one? It's not reasonable. So this is the assumption that it's indeed reasonable. It makes the whole treatment very simple. So it's also useful, but it's also reasonable to assume it. So let's assume that it's Gaussian. But if you ask me, is this assumption strict? No, you could avoid it. But, you know, I'm not sure it's reasonable. So a second assumption is that they have to be Gaussian. And let me introduce a third assumption. What is the purpose of this relationship? Is to explain the memory. Okay? So basically, before then writing this, you have drawn the autocorrelation function of U, and you found that there is memory. So the purpose of introducing this linear relationship is to explain the memory. Of course, if it is well explained, then you are happy. If it is not well explained, you are unhappy and you have to change the model. So, a necessary condition for this model to be reasonable, to be working, is that you explain the memory in your Qt through this linear relationship. How can we check this? There is a very simple way to check this, by thinking at this process, and in particular think at this random variable, which is I introduced as an error, okay, measurement error, or whatever, it's estimation error. An error, epsilon, is an error that is it correlated or not? So let's assume that the error still has memory. So I start from a variable that has memory. I introduce a linear relationship to explain the memory, and then I find that the linear relationship doesn't work well because there is an error. If the error still has memory, what does it mean? It means that my attempt to explain the memory was a failure. So if epsilon still has a memory, it means that this linear relationship is not capable of explaining the memory of the river flows. So a necessary condition for this model to be reasonable is that this error, find that it's there, find that it's an error, but shouldn't have any more memory. So third, epsilon t, capital letter, independent. And rho epsilon and against L, you draw the autocorrelation function, you find 1 at lag 0, but then you find the autocorrelation function lying within the bands. This is your test. And if not, change the model. This is not good. I call epsilon error. In the textbooks, it's called more technically residual or noise, or white noise. Usually, if you look at Wikipedia, you will read epsilon is a white noise. So let's don't be concerned about the terminology. White noise means just independent error. If you click in Wikipedia white noise and you see the definition, it's independent error. To be more precise, epsilon is defined as independent and identically distributed. I'm not concerned about identically distributed, but just to let you know, very often you find the acronym IID. So basically in some books and also on the web you may find epsilon is an IID random variable, which means independent and identically distributed. Identically means that the distribution doesn't change. Neither the shape nor the parameters. Okay, now your question could be, okay, let me suppose that I have a series of numbers. How can I estimate this model? Estimate means that I have to estimate phi1. But not only phi1, I have also to estimate epsilon. Because, of course, if I want to draw the autocorrelation function, I need to get the values for epsilon. So now let's suppose that you have a series of numbers, like the ones that I gave you, river flow. And the question is how to estimate epsilon and phi1. It's very simple. Not to say that in R there is a one function, a single function, that makes everything for you. Not to say that, but even if you had to do it by yourself completely, it's very simple. So now let me introduce how to do this. Okay, so we start from a series of observations. Q, T. And let's suppose that you use Excel, just because you know Excel has the advantage that you see the numbers. In R you don't see the numbers, you just see the console, and that's it. In Excel, let's suppose that you put the numbers QT in a column, and then the numbers go, let's put an index here, T, and let's suppose that it starts from 1 and it goes to N. Now let's suppose that in a cell, you write phi1 equal to, and then here, let's start with a trial value 0.5. For reasons that I will explain later, phi1 is varying between -1 and +1, with the extremes excluded. So the absolute value, it can be proved, we will prove that the absolute value is lower than 1. So this is why I start from 0.5, just trial coefficient. And so if I define the trial value for phi1, it's very simple for me to write here qt plus 1. And let me write qt plus 1, or let me write here phi1 qt plus 1 in another column. And of course, you cannot start from the first data, but you can start from the second one. Because the first you don't have the previous value. So you have to start from, you see, t plus 1 is 2. You start from 2. But you can get until n. This is very easy because you fix the value of phi1, and so you get here. And then here you can compute epsilon. And you can compute epsilon even at the first value if you assume that the first number, in statistics, remember that when you have to guess a number and you don't have any information, but what can you do is to guess with the mean value. So in this case, we cannot reproduce this value here at the first time step, so let's guess its value, which is 0. The best guess is the mean, and the mean is 0, because by assumption. So now I can compute epsilon, and epsilon is computed very simply in qt minus phi1 qt plus 1. So you have the sequence of the estimated epsilons. Now, this is very easy, as you see. The problem is that you are not sure that your trial value for the coefficient, this is called autoregressive coefficient. You are not sure that its trial value is correct. So how can I judge if the trial value is correct? First of all, this is a model where I have a relationship here, which is deterministic, plus an error. I have, of course, the interest in making this error as small as possible, because I want to maximize the part of qt that is explained by the linear relationship. So one trick is to find the value of phi1, which makes epsilon as reduced as possible. And one possibility is to compute the sum of from t equal 1 to n of epsilon squared p. And this can be done in an Excel cell. You take the sum of the squares of this column. In Excel, to do that, it's easier to make another column with the squares, and then you take the sum of the column. But anyway, it doesn't matter what is, it doesn't matter how you structure the Excel file. The moral of the story is that you have to compute the squares of the errors and sum them. And then what you can do is to change the value of the autoregressive coefficient until you get a minimum for the sum of the epsilon squares. This is what you can do. Okay, then when you find the minimum, you have your best estimate for phi1. In English, they say phi or phi for this Greek letter. You don't know?
Phi is phi.
Phi, okay, good, thanks. And I said they say because I guess that there are native speakers here. Are you native speaker or the three of you? No. No, not native speaker. And you are also foreign students, or yeah, and you are not native speaker, okay? Unfortunately, because otherwise you could teach me and us in general. But anyway, you can teach for sure in any case, even if you are not. Anyway, so basically, once that you minimize the sum of squares, you get a best estimate for phi1, and also you have estimates for epsilon. And then you can compute this autocorrelation function. And if it is within the bands, you are fine. And you already built your model. Your question could be, can you please tell us what is the probability distribution at each time step of Q? How can I compute the probability distribution? Okay, there is an obvious reply, which is it's Gaussian. Okay? But you may ask me, and what are the parameters? Meaning, what is the mean and what is the standard deviation? Of course, you know that the overall mean of Q is 0, but the mean changes because, if you have a high flow, then you get a mean that is above 0. And if you have a drought, you have a mean that is below 0. Okay, then what is the probability distribution? The probability distribution is Gaussian. So in general, Qt, capital T, capital Q, is normal. This means equality distribution. And N means normal. And what is the mean value? The mean value is Qt, lowercase, so the mean value is given by this relationship here, lowercase, and the standard deviation is sigma epsilon t. Why that? Because the deterministic relationship explains the progress of the mean, but you have a variability through this estimated mean. And the variability is given by epsilon. Epsilon changes. Once that you fix the t, epsilon can have several realizations and dictates the variability around the estimated value. Of course, I could provide analytical proofs, and I don't want to do that, because basically I almost concluded, and now of course I have to make a summary and also give to you on Thursday some additional details, but I don't want to give the proofs, the statistical proofs of what I just said. What I invite you to do is, and we will do this together, is to make experiments. So if you make if you take basically the simplest way is to generate random numbers through R, and then multiply the random numbers by phi1, Gaussian random numbers. You multiply these random numbers by phi1, and then you add to any result another Gaussian random number, and if you then compute the average at the standard deviation, you will see that it's that. Questions? Because I saw that you were, yeah, please.
The meaning of this relation.
This one?
Yeah.
It's just to provide to you with the probability distribution. So basically, I indicated here a random variable. And the random variable, the probability distribution, this means the quality distribution is Gaussian, and this is by assumption. And the mean value is given by the autoregressive relationship. And the standard deviation is the standard deviation of the random error.
Lowercase, what does it mean?
It means that this is the actual number. I told you that the difference between the capital Q and the lowercase q is that the capital Q is the random variable, while the lowercase is what you get at each time step. Okay. I think probably I should write. Okay, let me write it this way. Probably there could be a more clear formalism. I'm not sure, but let's write it in this way. Okay, now to move forward, first of all, I think it is clear that in this way, given the numbers that you have, given your observation, you can estimate the autoregressive coefficient and the random error. Now to move forward, I should explain to you, which is very simple, how to generate data, because this is our final aim. I prefer to postpone this to Thursday, okay? And I think that by explaining to you how to generate data and by making an exercise on Friday, I think that the full setting will become clearer. And also, as I said, we have some more details to explain to you, just fine-tuning, but we are almost getting to the target. Okay.